So welcome to section 4. We're almost done this series of the chapter A2.1 on groundwater monitoring with GRACE. So section 4 is really about learning to import a table of surface water storage. Again, these are basics of Earth Engine that you've probably learned before, but it's really the application and the content that is changing. So this graph is what we're going to produce, and we're going to chart surface water anomalies, which are going to end up being similar magnitude to soil moisture anomalies, looking specifically at the droughts I mentioned last time, same as the soil moisture. And especially you're looking here at your y-axis to see the magnitude differences and similarities. And then there's a surface water decrease during each drought, as I mentioned, and then the reservoir storage declines show that use is greater than the inputs during each period. So let's see what that all means. So for this section 4, you're going to be using checkpoint A2.1E. So as I mentioned, you go to the checkpoint that you need. It's a lot less complicated than a A2.1D, but for A2.1E, you're just going to use the section that you require, like here, copy and paste into your new script, and let's look at it. So before reading the table of reservoir storage, we compute the area from the combined HUC8 basins. So why we're doing this is because reservoir storage data from the California Data Exchange Center, CDEC, facilitated computing surface water storage anomalies for the Sacramento-San Joaquin Basin. Surface water storage, unlike other components of water storage, is not represented in land surface models. Instead, this type of storage is sourced from in situ observations. So here, the reservoir storage observations were summed for the Central Valley, and then total converted to annual anomalies to directly compare with the surface, the snow water and the soil moisture. So before reading the table of reservoir storage, we have to compute the area from the combined HUC8 basins. We used HUC at the beginning, HUC4, to find our basin specifically for the Central Valley. But the HUC8 are some sub-basins from the watershed boundary data set, and we're going to compute them together to create our area, in which we're going to look at surface water storage. So this is what's happening here. You're just extracting the geometry to convert time series of anomalies in kilometer cubes to centimeters. Then the imported res table is converted to an image collection of constant values to facilitate combining the data with GRACE and GLDAS resolved water storage anomalies. So you've got, first of all, the res table, and then you want to convert the CSV to an image collection so that we can actually layer it and work with it. Once we have our variables, what we can do is plot the surface water in equivalent units of centimeters per year, because we have been working in centimeters for water depth. So this is what's happening here, is that we're creating a loop so that we can convert the CSV to the image collection. And then we're going to plot, as I mentioned, in equivalent units and create a time series of surface water anomalies so that we can get a chart to work with. So again, we're creating a scatter chart, and we're using the 2003 to 2016, and we're using the same colors, same units, but this time we're looking at surface water. So let's run it. Now we've got this chart. Let's look at the surface water anomalies. What is happening? So the chart is showing that surface water anomalies are similar magnitude to soil moisture. As you can see, areas where there are droughts, same thing is happening. If you look at the y-axis, pretty similar magnitude if you compare to snow water, for example. So it's expected soil moisture, surface water, it decreases during each drought period in California, and these reservoir storage declines just show that the use is greater than inputs during each period. And now, looking at this chart that we've created, we're going to move on to the next step, which is combining the previous data sets to resolve changes in groundwater during the period of record. So it's still hard to quantify change without having all the variables in one plot, but it might be best to compute the differences via the equation that I showed earlier in the slides from the first part. So we're talking about this equation. So that's what I'm going to move on in section 5. But section 4 is really just about our last chart on surface water as we did for soil moisture and snow water. So far you should get an understanding of how we're plotting these and that it involves a time series, a linear trend, some conversion, which will involve somewhat of a loop so that you can apply to the image collection because you're dealing with more than one image layer. And sometimes you're going to need a loop to convert a CSV to an image collection because, as we mentioned, the surface water is made out of in situ observations. So let's move on to section 5, and that'll be one of our last parts. So following section 4, we're going to look at combining image collections. So this is looking at all the work that we've just been doing. We're going to learn how to combine multiple image collections and compute differences via an expression. If you recall, I keep mentioning this equation, so we're going to rearrange this equation to solve for groundwater, because this is the last part, is groundwater monitoring, which is part of this chapter, A2.1. And as I just mentioned, we're going to resolve groundwater storage changes in the basin by rearranging the equation. And this chart shows how reliant California is on groundwater. The chart shows large declines during a recent drought period. So we've been talking a lot about these droughts. We've observed this in the surface water anomalies. We've observed this in the soil moisture, not as much as the snow water because we're seeing peaks in the winter months usually. But still, we can see some sharp declines around these droughts times. And this will definitely affect the amount of water that's available, especially if we're using a lot of water. And especially for looking at areas like we had mentioned on our map that suffer a lot more in terms of water usage. So going into section 5, you're going to make sure that in your code, you're copying the A2.1 checkpoint, which is going to be at the bottom of the script. This is the last checkpoint that you are going to copy and paste. And then once you've copied and pasted into your new script, we can start. And basically, if you recall, we did originally, if you can remember from section 3, we had aggregated monthly GRACE observation data to annual average estimates to improve efficiency. In this case, you require annual means for the spatial joins since it calls for GRACE year later on. And we've been working on a yearly basis, so it just makes sense. And it's important for you to copy paste from the checkpoints so that you can make sure that you have all the necessary code. So we're going to be combining the GLDAS. So if you remember, that's our soil moisture, that's our snow water. We're going to combine the reservoir data, which is basically what we had done in section 1, looking at the reservoir in California's Central Valley specifically, giving us water data for the basin. And then we're also going to join the GRACE data. And that, if you remember, was in section 2, looking into total water storage. So this is really where we combine all the previous sections together. That's why it was so important to know how to do the previous sections and know how to import different types of data and know how to plot them, add them as map layers, just so that then when you get to the last section, you already kind of know what's going on. And your main focus is really doing the spatial join, and we're going to do a bit of map. So first, we're setting up the join. Let me just take my camera off so we can look at it better. So we're joining the GLDAS collections together using the EE join inner function. If you've done other chapters before, you should be pretty aware of how this function works. So I'm just going to skim over it. So here you're combining the GLDAS and GRACE data to compute change in human accessible water. You're creating the join, and then you're joining the GLDAS data. These are the variables that we had named earlier when we were working in the GLDAS script. And then the reservoir data, again, from the script that we were working with earlier. And then you're repeating the steps to join the GLDAS, but this time you're adding GRACE. So the GRACE year is what we had created way, way earlier back in section 1. Let me see if I can, in section 2, right here. So as you can see, we're just reiterating our variables so that we can do our join. Now the next step is going to resolve groundwater storage changes in the basin. If you want to make sure that everything's working, I recommend that you print first the image collection of the GRACE and GLDAS and Reservoir join. So let's just see to make sure that everything's working. Okay, so as you can see, for example, when you see your joined image collection, in here, it's probably going to just be, yeah, your GLDAS. But then when you go in here, you're going to check whether or not everything's there. So if I look at an image, for example, look at the properties, okay, look at the bands. We've got the SWEA, that is our snow water, SM, which is our soil moisture, SW, which is our surface water, and then TWSA, which is our total water storage from GRACE. Now, where it could not work, perhaps, is if you forgot to do this part, which is the annual means. That might create an error in your script, so just make sure that you have this, and this will usually come from copy pasting these. So moving on, we're gonna map an expression across an image collection to produce a new variable, because we're looking for groundwater anomalies now. And so you're basically taking the image collection that you created here, resolving for GWA, which means that you're solving these equations and you're selecting, remember, the variables we had seen, and you're basically just rearranging this equation as you would do normally using this. So you're basically isolating GWA so that it becomes this. And we're just assuming canopy water storage normally. So that's why it's not in here. Just assuming that canopy storage anomalies are very small relative to other storage components, and we're just ignoring them in the equation. So then you get an equation that would look like this. I'm just going to comment it, but it's basically going to solve for GWA, and then you're going to print GWA. When we run it, we'll see it. And then we can now plot to see how groundwater storage is changing, because now we actually have values for groundwater. So like we've done in all the other sections, you're going to plot the results, and then we're going to title it changes in groundwater storage. Again, we're filtering by date, keeping it to 2003 to 2016. And then we have our chart. Once you have that chart, you can estimate how much groundwater was used during the 2012-2016 drought period. And in the console, we'll see. Let's just print it and see what we get. So basically up here, what we've been doing is mapping an expression across an image collection just to produce this new variable, groundwater anomaly. And now you can see that the variable IMG is being used to extract bands from the combined image collection that we just did up there. And we're creating a new one with just one band. And this is how we're able to plot it below. So let's look at it in more detail. So as you can see, let's say we're looking at our drought period right here. You can see how reliant California is on groundwater. The chart is showing like a really large decline during recent drought periods, like right here. And from this chart, you can then estimate how much groundwater was used during this drought period. So now we have our chart. And from this chart, as I mentioned, we're able to estimate the groundwater that was used during the 2012 to 2016 drought period, just to see how much California has lost. So how we do that? We go here, let's say we jot this down. January 1st, 2012, we're looking at minus 3.875. So, and then 2016, we're looking at minus 16.925. So I've put these two values here based on the drought period numbers we found. And this, again, we're looking at annual data. And from what we see, if we then do the conversion to kilometers and then do it over the area in kilometer squares, because we're looking for kilometer cubes, so this is why we're doing the conversion again, then we just do this equation in code, and we can just print what California has lost in terms of groundwater during the drought. And lost kilometer 3 is our variable we just did. So then with these values, I'm just going to change them so they're accurate to what I have. Let's see what this gives us. Okay, so during the 2012-2016 drought, California lost 20.28 approximately kilometer cube in groundwater. So now you know from this chart, and this chart was created from all the different sections that we created with the soil moisture, the snow water, the GRACE, which is giving us the surface water, and thanks to all that we've done before, we're able to have the data for this equation, assuming canopy, water storage, so that we can solve for groundwater. And then with this other small equation, doing the conversion, putting it over the area specifically of the basin, then we can have an estimate of groundwater. So you've done it. You've got resolving groundwater storage changes in the basin, getting an estimate of what the California lost during a specific drought period, just showing how reliant California is on groundwater. And to conclude, we've done many things. So you've reviewed GRACE observations. They're used to estimate changes in water storage for regions like California's Central Valley. GRACE is specifically very efficient for large river basins, as I've mentioned earlier. You've combined data sources. We've combined GRACE. We've combined image collections. GRACE is equivalent water thickness observations, model simulations of soil moisture and snow water equivalent, and in situ reservoir storage observations, because that allows you to get the surface water, if you remember correctly from one of the previous sections. Then we go into quantified groundwater storage declines. We were able to demonstrate how to quantify groundwater storage changes because we were able to solve the equation for groundwater using all of the combinations of image collections. That's where we also did the join. We did a bit of math also to make an estimate of what was lost during a specific drought period. And by looking at all of these graphs, you're also able to determine things like these, like when would a drought period occur? What's the difference in magnitude between snow water and soil moisture, for example, or even total water storage, and understand how that works. So these are really basic hydrology applications in Earth Engine, looking at a specific region. And there's also some involvement of advanced Earth Engine skills, creating an image collection from a table. Remember that CSV conversion, and then joining multiple image collections. And so these skills and methodologies can be applied to other regions globally. But remember, there's a few things that you do have to follow if you are going to apply it to another study region. But all of that is in the chapter in the book specifically, which I provided the link at the beginning of the slides. So I hope that this was pretty informative and that you were able to apply it to other regions and other applications in Earth Engine.